The imaginary number is the solution to the equation x. The solution to the equation x squared plus 1 equals 0. If you try to solve this problem, you get that x squared is equal to negative 1, which hopefully you already know that any number squared cannot be negative. So I tried to take the square root, and there is no answer. And so what we decided to do, or someone decided to do, was, well, let's just make up a number. And that number is called the imaginary number I. I is special in that it has two key properties. One, the square root of negative 1 gives us I, and that I squared is equals to negative 1. I is the only number that when you multiply by itself, the answer is negative. All other numbers, when you multiply by itself, you get a positive answer. And that's what makes I special. Now let's take a few minutes to just look at complex numbers. A complex number is one that can be written in the form a plus bi. A is called the real part, and I is called the b is called the imaginary part. Complex number such as this right here, 3 plus 0i, is said to be real because 0i simplifies just to 0. And a complex number with a 0 imaginary part, 3i, is said to be imaginary. That immediately means that all real numbers are complex numbers as well. Complex number written in this form is said to be in standard form. Let's go ahead and do the 4 operations on your complex numbers. Addition. If I have 2 plus 3i plus 4 minus 6i, 2 plus 3i plus 4 minus 6i, you simply add like terms. The 2 and the 4 gives us 6. The 3 and the negative 6 gives us negative 3i. That's how you add. Subtraction is the same, except you distribute the minus sign. So if I have 2 plus 3i minus 4 minus 6i, you will get 2 plus 3i. After I distribute the minus sign, I get negative 4 plus 6i. And now, I group like terms. The 2 and the 4 is a negative 2. And the I and the I, the 3i and the 6i gives us 9i. Because as you know, 9 i's are better than 1. Yes? No? No? I don't think so. Multiplication is just as straightforward. Let's say I have 3 minus 2i multiplied by 4 minus 5i. Right here, you just distribute using the FOIL technique to get the answer. So 3 times 4 is 12. 3 times negative 5i is negative 15i. 2i times 4 is negative 8i. And then 2i times negative 5i is plus 10i squared. We have some simplifications to do. So this right here is 12, negative 15, and negative 8 is negative 23i. And then plus 10, but I plus 10, but I squared is negative 1, right? I is the only number. When you multiply it by itself, I squared, you get a negative answer. And so you get this right here. And so this is 12 minus 23i minus 10, which is simply 2 minus 23i. Hey, 23i. There we go. And that's how you multiply. That's how you multiply your complex numbers. Notice that when you multiply 2 complex numbers, you get another complex numbers. The I squared is key. You have to remember that I squared equals negative 1. Now, before we can do division, we have to stop on a short topic called the complex conjugate. The complex conjugate is simple. If I have a complex number 3 minus 4i, then the conjugate is denoted by a bar above the complex number, and the conjugate is going to be 3 plus 4i. To find the complex conjugate, you simply change the sign on the imaginary part of the complex number. So if I had, say, 2 plus 5i, then the conjugate would be 2 minus 5i. If I had 4i as my complex number, then the conjugate would be negative 4i. If I had 10 as my complex number, then the conjugate would still be 10. Again, we change only the sign on the complex number. Well, why do we care about the complex conjugate? It has many uses, but the most practical use of the complex conjugate is that if I multiply a number, 3 plus 2i, times its conjugate, 3 minus 2i, the result will be an entirely real number. The i's will vanish. 3 times 3 is 9. 3 times 2i is minus 6i. 2i times 3 is plus 6i. And then 2i times 2i is negative 4i squared. When I'm simplifying, these two will cancel out, and that is a direct result of the signs being opposite. The opposite sign makes these two signs opposite, and so these two will always cancel out. And so that will leave me with 9 plus 4, because as we all know, I squared is equals to negative 1. And 9 plus 4 is 13. There's a nice little shortcut. If I have complex conjugates being multiplied together, a plus bi being multiplied by a minus bi, the result will always be a squared plus b squared. Kind of like your Pythagorean theorem. In fact, when you do a lot more complex numbers, you'll see that that Pythagorean identity shines through quite a bit. Right, and so if you look right here, 3 squared is 9, 2 squared is 4, a plus bi. Alright, so that's the first part. Those are your complex numbers. Let's go ahead and look at our complex solutions. First thing we have to know is how to handle complex numbers. If I want to take the square root of negative 36, what I first do is I write it as 36 times negative 1, and then I take the square root of each piece. The square root of 36 is 6, the square root of negative 1 is I, the square root of negative 36 is 6i. A nice way to think about it is that the minus sign becomes the I. Right. The minus sign becomes the I. And of course we can check our answer. 6i squared is 6i times 6i. 6 times 6 is 36. I times I is I squared. But I squared is negative 1. So you get your negative 36 back. If you have a number that's not a perfect square, that's alright. Take the square root of negative 45. Again, you split out the minus part. 45 times negative 1, square root. Well, the square root of negative 1 is just going to be I. While 45, I got to break down. That's 9 and 5. I need to have at least one of the numbers be a perfect square. And then I radical, and so that's 3 radical 5. I. Traditional is written as 3i radical 5, but this way is also acceptable. 3 radical 5i or 3i radical 5. Either way is fine. But that's how you simplify when you have a negative sign under the radical that doesn't break down nice and neat, like in the first example. So with that, let's solve this problem right here. Solve for x. You may have real or complex solutions, so give all solutions. And so I have 3x minus 2 squared plus 12 is equal to 0. This is an equation in standard form, and so I just got to unwind the equation so I can get my answer. So I will subtract 12, subtract 12. I will divide by 3, divide by 3. And that gives me x minus 2 squared is equals to negative 4. And this is where the complex number comes in. When I radical both sides, before I would say, well, there is no real solution because I cannot take the square root of a negative number. But, I now know the answer is going to be plus or minus, of course. I am solving an equation. I want all the solutions. So I have to remember that the radical is plus or minus, and not just the principal root. And the square root of 4 is 2. The square root of negative 1 is I. 2 i's are better than 1. And the last step is to add 2 to both sides. And so I get that x is equals to 2 plus or minus 2i, or 2 plus 2i and 2 minus 2i. Notice that this is a complex conjugate pair. Oh, yeah, complex conjugate pair. Which is something that happens quite often when you're looking at your complex numbers. Let's look at another example. Let's say I have x squared minus 6x plus 25 is equals to 0. And I'm trying to solve this thing right here. But this time I'm going to solve finding all solutions by completing the square. So the first step is I'm going to remove the number that's in my way. Remove that 25. And I have x squared minus 6x. I have a space is equals to negative 25. Now to figure out the number that comes right here, I have to take this number and divide it by 2 and then square the result. Negative 6 divided by 2 is negative 3. Negative 3 squared is positive 9. So I add plus 9 on this side and I add plus 9 on that side. The perfect square trinomial we have right here factors into x minus 3 squared. Remember, you take the square root, then the sign, then the square root, and the other side is negative 16. And from here, this is just like the previous example, square root, and go home happy. Radical, radical, and so x minus 3 is plus or minus 4i, and then I add 3 to both sides. And so I get x is equals to 3 plus or minus 4i. Again, another conjugate pair. Complex conjugate pair. Of course, you could solve this same equation using the quadratic formula. Remember that formula from way back when? Back in the day when life was happy? And then all you want to do was use that lovely formula because it always gave you the answer. Let's try the same problem again, but using the quadratic formula this time. So, solve x squared minus 6x plus 25 is 0. And the complex is x is equals to minus b plus or minus the square root of b squared minus 4ac all over 2a. Plug in, so that's negative 6 plus or minus the square root of 6 squared minus 4 times 1 times 25. Oh my goodness, that's huge. Divided by 2 times 1. That gives us 6 plus or minus the square root of 36 minus 100 over 2. 36 minus 100, I've seen that before. Right. 64. 6 plus or minus the square root of negative 64 over 2. And then I can simplify. The square root of negative 64 is 8i. Square root of 64 is 8. The square root of negative 1 is I over 2, and then I simplify. I can factor out a 2 from the top, so that's 2, 3 plus or minus 8i over 2, and then, factoring out, that's a 4, plus or minus 4i after I factor out the 2, and then my 2's cancel, and lo and behold, I get the same answer. 3 plus or minus 4i. This result right here leads us to a very, very important result. The reason that I got an I in my solution is because this number was negative. Right? The square root of negative 64 is what gave me the 8i. That's when the I first appeared. The negative 64 comes from this part of the quadratic formula, the b squared minus 4ac. Right? If this was not negative, I would get no complex solutions. And so because of that, we call this b squared minus 4ac the discriminant. It discriminates amongst solutions. It tells us if our answer is going to be complex or not. If it's a negative number, it's complex. If it's not a negative number, then we only have real solutions. And so, because of that, this right here follows some basic rules. If the discriminant of b squared minus 4ac is less than 0, like what we did a while ago, you get two complex solutions. In fact, in our examples, because we have real coefficients, we get complex conjugate pairs actually. Two complex numbers, one for plus, one for minus. If b squared minus 4ac happens to exactly be 0, then you only get one real solution. It's really sad, I know, but true. Only one answer. And if b squared minus 4ac is greater than 0, then I get two real solutions. And when I say real solutions, I mean the answer doesn't have an I in it. It is not complex. Alright? As they say in the business, happy hunting.